In this video, before we get to know automated methods for hyperparameter optimization, we'll discuss how we can actually do this manually. This is very relevant in practice, since it is useful to be able to diagnose poor hyperparameter settings by hand. Manual hyperparameter optimization might be tedious when you do it a lot, but doing it a few times is very instructive and gives you a deeper understanding before you start relying on automated tools. So let's dive right in. Manual hyperparameter optimization in deep learning. Let's start with some motivation for why we discuss manual HPO, if there are automated methods available for this problem. Firstly, I would like to emphasize that if you really want to understand deep learning methods, then you also need to understand the hyperparameters. For example, how these hyperparameters affect things like training and generalization error, training speed, and the memory requirements of your neural network. For example, let's have a look at what these hyperparameter settings here will do to these characteristics. So firstly, if you reduce the L2 regularization strength, then your training error, well, that will probably go down, while your generalization error might go up if you need the additional regularization that you just reduced. The training speed, that won't be affected much, but you might actually train a little bit faster, since the regularized loss function is a bit smoother than the unregularized loss function. And finally, the memory requirements won't be affected at all. Now, if you increase the network's depth, then you will typically reduce the training error if you're training for the same number of epochs, but your generalization error may go up or down. Well, that actually depends, as we'll see later. Training will be slower, since each forward and backward pass through the network takes longer, and your memory requirements, they increase. So we walked through the effects of these two hyperparameters here now, but similarly, it's instructive to go through these effects of all the other hyperparameters that you're encountering while optimizing your neural network performance. So another motivation for manual tuning is that if you do this well, then this can actually be very sample efficient and even better than automated HPO methods. But for that, you really need to know what you're doing. And if you become an expert at manually tuning your hyperparameters, then you can probably codify what you're doing into an automated HPO method. And finally, even if you just want to use automated HPO tools, then the knowledge gained through this manual experience is very helpful to help you with the various decisions for setting up automated HPO, such as, well, which hyperparameters should you actually tune, which fixed values should you use for the others, and which ranges should you consider for each of the hyperparameters to be tuned. So let's now have a look at the classical view of how generalization error depends on the capacity of our networks. So if you plot the generalization error on the y-axis here and the capacity on the x-axis, then by changing a single hyperparameter, we typically get some sort of U-shape, like this here. On the left side here, we have low capacity, and the training error is usually still relatively high, while the gap between the training and validation error is relatively low here. So we're in the underfitting regime, where the training error is still too high. On the other side, we have high capacity. The training error is usually very low, but the generalization error can be large. And so we're in this regime where there is a big gap and we're overfitting. The optimal model capacity, well, that is a point that gives us the lowest generalization error here. And well, this here was just a recap from a standard machine learning course. Now what is plotted here, that's actually an interesting point. That is the effective capacity. This is a function of the network's representational capacity, which is influenced a lot by the network size. but also by our optimization algorithm's ability to actually use that representational capacity. So for example, when our optimization is not working well, or when we regularize really strongly, then our model's effective capacity is lower. So while we just reminded ourselves of the classical view that we get more and more overfitting as the effective capacity grows, the folk wisdom in deep learning is actually that bigger models are always better. So how does that fit together? Well, there's actually recent evidence that generalization error as a function of your effective capacity first decreases, then increases, and then decreases again. So what's plotted here is the error as a function of, in this case, the width of a neural network, of a ResNet. But that's actually just an example. And this paper down here by Nakiran et al. Shows a lot more examples, also actually including a similar effect with the number of epochs used for the optimization. Now, this critical regime here is where the model transitions from being under-parameterized to over-parameterized. So where the training error, here in green, just reaches close to zero. And we have just enough effective capacity to fit our data. From that point onwards, we're in the modern regime where actually bigger models are better. And up to there, we're in the classical regime where we're actually facing this bias variance trade-off. Having seen these different views, I now want to talk in a bit more detail about some measures you can take against underfitting and overfitting. If your training set performance is poor, in other words, you're in the underfitting regime, then you typically want to increase your effective capacity because it's too small. So in order to do that, you can check the following. First, check your representational capacity. So is your network large enough? Is it deep enough? Is it wide enough? Second, you can check the optimization algorithm's ability to actually minimize this cost function. And then you can also check your degree of regularization. So are you actually regularizing your cost function too much in order to, and by that actually reduce your effective capacity too much? And what you can then, of course, do is add more layers, add more hidden units to each layer, tune your optimizers, hyperparameters, especially the learning rate, etc. Getting this training error really low is key to being effective in deep learning. If your training error is only okay, that may actually not be good enough. If you don't actually use any regularization methods yet, then it should really typically go to almost zero as quickly as possible. Now, the other potential problem to take care of is overfitting, where you have strong performance on the training set but not on the validation set. And there's various options to tackle overfitting. The first one you would usually try is to assess different ways to reduce the model's effective capacity. So you would do that by reducing the model size or by trying different types of regularization. You could actually also, because of the double descent phenomenon, actually increase the effective capacity. So this is something that one has to play with, unfortunately. Now, poor test set performance can, in some cases, actually also be caused by software bugs. Now, this sounds really dumb, but with all the data augmentation and deep learning and with saving models to disk and loading them again, there's actually plenty of room for bugs. So you should make sure that you don't have this issue. And one simple way of checking this is to feed your training set through your model as a validation set, and to make sure that when you do that, then you get the same validation error as you get training error. Finally, one method to improve generalization that's not actually on the algorithmic side is to simply get more data. In some applications, that is actually quite possible. So what you can do in order to assess how much performance would improve if you had more data is to fit your model based on different subsets of your training data, and then plot training and test performance as a function of the number of data points. So you would have the number of data points here, and here you would have test set performance. So if that actually does something like this, then, well, you know that actually getting even more data, well, you probably would not actually get better performance because test set performance has already flatlined before. However, if your test set performance is doing something like this, then you could actually expect that you will get better performance by getting more data. Now, these considerations lead us to a practical approach against underfitting and overfitting that works as follows. So first, you make sure that you can fit your training data well. That's the most important thing to start with. You don't worry at all about overfitting at this stage, because if you can't even get your training error down, then you'll also have poor test performance if at training time you don't actually use a lot of regularization yet. And in this stage, you can actually use a small subset of the data so that this step doesn't take too much time. Importantly, you can actually tune most of your optimization hyperparameters already at this stage without ever looking at the validation set because, well, during training, you only look at getting the training loss down. And if you actually don't even do that, then, well, you actually need to change your optimization pipeline. So in particular, your learning rate, you can pretty much tune on this training loss. And then afterwards, once you actually can effectively get your training error to 0, then you can combat overfitting. So in this stage, you can assess how the model reacts to larger subsets of your data. You can monitor both training and validation performance, and you can play with different regularizations and the model size. And at this stage, you have to wait until this stage to optimize your regularization hyperparameters. Those wouldn't make any sense to optimize in this stage here because you're not actually looking at your validation score yet. And you're not looking at overfitting and at regularization and so on. So note that in all of this, the learning rate is really important. It's typically the most important hyperparameter, and whenever you change some other hyperparameters, then it's good to check whether you should also update your learning rate again. Since the learning rate is the most important hyperparameter in deep learning, let's talk about it in a little bit more detail. So the learning rate controls the effective capacity of the model, but it does so in a fairly complex way. If you have a bad learning rate, then you just don't use the full potential of your neural network and you don't use the full capacity because you actually just don't get the network optimized. The error still depends on the learning rate by a U-shape, but it's a pretty extreme U-shape here, going down and then sharply up. Typically, for learning rates, the optimal value is actually quite close to the point where you're almost diverging. So you're getting really better and better and better, and then at some point, if you increase the learning rate a little bit more, then you diverge. So that's actually why this hyperparameter is typically quite tricky to set. But a natural heuristic for setting it is to increase the learning rate ever more until you get to divergence, and then you go back a step. But especially if you set it too close to the divergence zone, then you really have to re-optimize it frequently when you change some other parts of your neural network. All right, that brings us to the end of this video. And as always, I'd like to leave you with some questions. I encourage you to pause the video here and think about them to activate the material. Thank you, and I'll see you in the next video.